Let's get to the fun stuff. How do we do calculus with our inverse trig? Let's work out differentiation. Now, the good thing is, what we can do is use the idea about inverse functions. If y is equal to the inverse sine of x, then x must equal sine y, and we know how to differentiate sine. So instead of finding dy dx, I'll find dx dy. So dx dy will become cos y. So dy dx is 1 on cos y. There's the derivative in terms of y. I guess it's more normal to see it in terms of x. So how do we transform it back? Well, the cosine y I change to the square root of cos squared. And then cos squared I can say is 1 minus sine squared. But hang on, x was sine y. And so I end up with 1 over the square root of 1 minus x squared. So there it is in terms of x. Let's do a similar one there for inverse cos. And so we'll turn it to x equals cos y. We know that when we differentiate cos we get minus sine. Turn it upside down, minus 1 on sine y. And then I'll just do a similar thing. I'll say, well, hang on. Sine is the same as the square root of sine squared. Sine squared is 1 minus cos squared. And we said x was cos y. So we get minus 1 on the square root of 1 minus x squared. Now it kind of makes sense that those two things would be similar, because remember, they're the same curve but shifted 90 degrees. So at the same x value, all it really means is one's going up and one's going down. Okay, what happens with tan? Inverse tan, make x the subject, we get tan y. Differentiate tan, we get sec squared. Turn it upside down, I have 1 on sec squared, but hang on. Sec squared is 1 plus tan squared, and tan we said was x. So we get 1 on 1 plus x squared, no square root sign. So they're the three basic ones. Let's generalise them. The way they're quoted is when it's just a linear function. And so they go inverse sine of x on a, differentiate it, and you get 1 on the square root of a squared minus x squared. Okay. Cos, you get the same thing, but minus 1 on the square root of a squared minus x squared. Inverse tan's where you've got to be careful, because you actually get a on a squared plus x squared, not 1. Okay? So you've got to be careful there. The other two have 1 on the top, but with inverse tan you have a on the top. Personally, that's not how I do it. Personally, I do it as just simply a function. So then it doesn't have to be linear, it could be any function. So inverse sine of function x is the derivative on the square root of 1 minus the function squared. Inverse cos becomes minus the derivative on the square root of 1 minus the function squared. But see, now with inverse tan, I don't have to worry about the numerator being different, because it's still the derivative on 1 plus the function squared. So each of those have the derivative on top. Well, it's up to you, of course, how you memorise those. So inverse sine of 5x. Now, I'd just look at that and go derivatives 5 over the square root of 1 minus the function squared. 5x all squared is 25x squared. I just think that's easier than doing x on a. Because if you did x on a, what would happen? You'd go 1 on the square root. What's a? No, a would be 1/5, wouldn't it? Because it's x on a. So you would have 1 on the square root of 1/25 minus x squared. But then you'd multiply, because you don't have fractions on fractions. I just think that's messy. So the only time personally I would use that x on a is if it is x on a number. Then okay, it's going to be quicker. But otherwise, I'm just going derivative over the square root of 1 minus the function squared. I mean, how much quicker is that? Bang, you got the answer, one line. So, minus the derivative. The derivative of e to the x is e to the x over the square root of 1 minus the function squared. Be careful when you square e to the x, it's e to the 2x. Okay. Now, alright, here I will concede. When it is x over a, it is quicker just to go 1 over the square root of a squared minus x squared. Okay? Because the way I'd do it, with the function one, I'd go, okay, the derivative over the square root of 1 minus the function squared, but I've got fraction on fraction. The denominator, it might not look it, but the denominators are actually the same. Because you'll see the top, the denominator is 3, the bottom is square root of 9, which is also 3. So I can rewrite that, multiply everything, and I end up with 1 on the square root of 9 minus x squared. So okay, as I say, I'll concede when the question actually is x over a, yes, that is a quicker way of doing it. 1 over the square root of a squared minus x squared. Oh, let's swap it the other way around. We had inverse cos of e to the x. Now we've got e to the power of inverse cos x. So it's an exponential that we're differentiating. So we differentiate the power, differentiate inverse cos x, I get minus 1 on the square root of 1 minus x squared times e, but don't change the power. So e to the power of inverse cos x. I think it looks a bit neater putting that e to the inverse cos x on the top of the fraction. Chain rule. Anarchy. Bring down the power. 3. Lower the power. 2. Diff the inside. Differentiate inverse 10x. We get 1 on 1 plus x squared. So let's make that look a bit neater. 3 lots of the inverse tan of x all squared over 1 plus x squared. Product rule. X squared inverse tan x cubed. Write down the first, x squared. Diff the second. So it's inverse tan of x cubed. So I'm going to go derivative, 3x squared, on 1 plus the function squared. I square x cubed, I get x to the 6. Plus, write down the second, inverse tan x cubed. Diff the first, 2x. Let's tidy that up. I'm not going to bother making that all one fraction. I think I'll just leave that one there. So 3x to the 4 plus 1 on x to the 6 plus 2x inverse tan x cubed. 1D, where you can have some playtime differentiating inverse trig.